Okay, so the question at hand is, which falls faster, a heavier object or a lighter object? Okay, so we have to be just a little bit careful. Exactly what do we mean by fast? Okay, which falls faster? All right, so when we talk about the motion of an object, that's its kinematics, so the mathematics of its motion. How do we describe it? And so there's two things we have to contend with whenever we're dealing with that. First of all is what we call the velocity. Oops, a little out of practice here. The velocity of the object, okay, which we'll write as a V, and then there's the acceleration, which we'll write as an A. Okay, all right. So if we think about what's happening with something that's falling, all right, so I've got my object here, okay, and if we look at that thing, there's some weight acting on that thing, all right, which is my force mg. Okay, so if I use Newton's equations, all right, Newton says what we can do is we can sum up all of our forces, and that's going to be equal to the mass times the acceleration. So if the only force that we have is the weight, okay, the pull of the earth, okay, then what we're dealing with is mg is equal to ma. Okay, and if you go back to your algebra, all right, you see we got two m's on both sides of the equation, and so that means they're going to cancel each other. Okay, and let me change this up just a little bit, and it says that the acceleration a is just going to be equal to g. Okay, so if the only force you have acting is the planetary force, okay, then that's what you're going to have. All right. So if you go to the moon, this is what you're going to see. You drop a hammer and you drop a feather at the same speed. This is what you get. Okay. And this was done on the moon. And in fact, that's what happened. And it is very, very strange to see. Okay, and you can just Google that, hammer, feather, moon, and you can find that video. I don't know if it was Neil Armstrong, but one of those guys actually did that. Okay. All right. Now, here on the Earth, though, we have air. Okay, we've got the air to deal with. So that means we have another force, and back here, and let me just say D for that. Okay, the drag force. Okay, now the drag force is going to depend on a lot of things. Okay, it's going to depend on the cross-sectional area of the thing. It's going to depend on the shape of the thing, and it's going to depend on the speed of the thing. Okay, now it could depend on the linear speed. It could depend on the square of the speed. It could be cubic. It gets complicated quick. So let's just make a super simple way to think through this. And let's just say that it's equal to some value a times the velocity, or its speed rather, okay, in this case. So now what's that going to do when we set up with Newton's equations? Well, what that's going to mean when we come over here is when we add up our forces, okay, we're going to have mg minus a times v, like this, okay? And so let's rewrite that just a little bit here. So I'm going to have ma is mg minus a over v. Okay, now what I'm going to do, I'm going to do a little bit of algebra here. I'm going to pass the m through on both sides so that we get a all by itself, because that's really going to be the key to answering this question about which one falls faster, is what happens with the value a, the acceleration. Okay, because if they're both going to fall the same, then we'll get the same value for a. Okay, if not, then we might get something different for a. So let's just see where this goes. All right, so we're going to get in here. We're going to divide through by m on all this stuff. Get back to your high school algebra again. And what I'm going to be left with is a is g. Okay, we saw that already. But now we've got minus a v over m, like this term here. Okay, that changes everything. All right, that changes everything. So let's think about what happens here when if we first start to fall. Okay, so let's make some axes here. Okay, so time, we'll put time there, and we'll put A here. Okay. Now, when we first start out, we have no velocity. Our velocity is 0. And so we're going to have 9.81 meters per second is going to be how what our acceleration is. Okay, 9.81 down. However, that's with no velocity. Okay, but as soon as we drop it, it begins to pick up speed. And what happens then is that this term here becomes larger and larger as v gets bigger. So over time, what happens is this acceleration begins to get smaller and smaller and smaller, and it drops off something like that. And it will actually, before too long, it's actually going to get down to 0, where a is actually 0. Okay. Now, once that happens, that's what we call terminal velocity. Okay. So the way we can work that out algebraically is we can say, okay, let's set a equal to 0. Okay, and let's work with that. So now I've got a new equation, a g minus av over m is equal to 0. Okay, let's do some algebra. I'm going to take my avm term to the other side. Okay, so I've got g is av over m. Okay, now I'm interested in the terminal velocity v. So I'm going to take my a and my m back to the other side. Okay, and the way I do that is I pull this trick right here. Okay, and that's going to cancel those terms. Okay, and so what I'm left with then is that my velocity is equal to g over a, okay, times m. All right, and so remember, a is just a sort of a shortcut way of talking about my coefficient of air resistance and my geometry all combined together. Okay, and then I've got the m on there. All right, and so what we can do then is we can say, well, let's think about that. Okay, in the sense of what is the terminal velocity as a function of the mass. Okay, and you can see that it's going to be a straight line with a certain slope like this. Okay. Something like that there. Okay. So if I had, let's suppose I take 2 bowling balls. Okay. And one of them, it's my control ball, and I leave it exactly how it is. And then I take its twin, it's identical, and I sort of core into it, and I pull out a plug, and I put some lead in there so that now this second ball, it's exactly the same on the outside, but it's much heavier. Okay, what I'm going to find then is, here's the control ball. Okay, it's going to have a certain terminal velocity here, whatever that might be. Okay, maybe, I don't know, maybe that's, I don't know, I'm not going to make up numbers, but then my ball that I've modified is heavier. It's over here. It's going to have a higher terminal velocity. Okay, so all things being equal, the heavier object is going to have a higher terminal velocity. Okay, another way to think about this is with kinetic energy. Okay, so both balls are falling, they're picking up kinetic energy. Air is bleeding that kinetic energy away. Okay. And sort of imagine it kind of like this. Okay, this is really hand wavy here, but so if you've got a heavier object and a lighter object, okay, the lighter object doesn't have as much kinetic energy potential, okay, in order that the air can bleed off. Okay, so the air can bleed that energy off pretty quickly. The heavier objects is going to develop more kinetic energy, and so it's harder for that to bleed off that way. Okay, you could also think about it in terms of momentum and what we call impulse, which is the force and the time that's involved there. Okay, but there's the long and the short of it. Okay, so all things being equal, the heavier object will fall faster. Now, that's the tricky part. Are all things equal? So if you're dropping a Hyundai and you're dropping a Mercedes, are all things going to be equal? Well, maybe. They'll be pretty similar, okay? As long as they're similarly sized cars. with similar wind profiles, that sort of thing, then they're going to be pretty similar. And so you would expect a heavier one to hit the ground a little bit ahead of time. Okay. Yeah, but I mean, is it going to be a measurable amount? Hard to say. You're going to have some way of guaranteeing that both cars, as they fall, will maintain the same orientation exactly. Okay, so that's tricky too. All right, they might behave slightly. They might have the location of the center of mass relative to the vehicle might be slightly different, and that could cause them to flutter in different ways. That could be unpredictable. It can be hard to do there. Okay. All right. So anyway, there you go. A sort of fun bonus is to think about cats falling out of off of balconies of very high buildings. Okay, because our terminal velocity equation here. Okay, guess what? That works for cats too. The thing is, a cat can't control its mass, but it can control this value A, depending on what it does with its body. So if you look statistically at cat damage, and veterinarians have done this as a function of height, the height where cats are most likely to sustain severe injury is around 6 stories. Okay, so the amount of damage a cat gets increases. So let's see, maybe I can make that graph here. All right, so we're going to put a number of floors here, and we're going to put cat damage over here. Okay, and what you see is cat damage goes kind of like this. All right, and then suddenly it drops off like that. Okay, and so it was kind of a puzzle for a long time. What the heck is going on with the cats? And the fact that the cats can change their profile as they fall is the solution to that. So when the cat first falls out the window, it begins to accelerate. Okay, it goes faster and faster, but it has that feeling of free fall, just like we have when you're on a roller coaster or something. All right, sort of the cat then sort of panics, loses its sense of orientation, and it curls up into a ball because it's afraid. When it does that, then its value for A is much smaller. Okay, and so its terminal velocity is going to be, fairly high because A is in the denominator. If that gets small, V is going to go up. All right. However, once you reach terminal velocity, then your object, bowling ball, cat, whatever it is in equilibrium again. Okay, all the forces are balanced. And at that point, the cat doesn't have that weightless feeling anymore. It can figure out where it is and what's going on. And as soon as it does that, it sort of relaxes and it puts its little legs out like this and kind of turns into a cat parachute. All right, then the value of A goes way up. Okay, and the cat will actually begin to slow down just like a regular, like a person with the parachute. It slows down to a lower terminal velocity. Okay, so at some point between this height and this height, the cat achieves a new, much lower terminal velocity, and it can land with relatively low risk of injury. Okay, well, anyway, there you go. So I hope all that makes sense. All right, just like that. It's pretty complicated. It's difficult. A lot of people don't get this right. Okay, but hopefully that works for you.